Newton's second law of motion. Let's get started with this. In Newton's second law of motion, there appears a term called momentum. We're going to study momentum later. Now I'm just going to introduce this to you so that you know what momentum is. Momentum is represented by P, and momentum mathematically is mass into velocity. Momentum of any body is mass of that body into velocity of that body. Momentum is a vector quantity because velocity is a vector quantity and the direction of vector will be the same as that of the velocity. Now, the reason why we define a quantities like that, mass into velocity, there are various reasons for that. And just to give you a little idea about it, suppose there's a block kept on a surface. This block is moving with certain velocity. On its way, there's another block which is at rest. Now, when this block is going to collide with this block is going to gain some velocity. We all know that. So, but the velocity gained by this block depends on the mass of this block and the velocity of this block. If another block is coming with the same velocity but a lighter one, a smaller block, then the velocity that this block will gain will be considerably less. So, and if a larger block of the same velocity is coming and colliding with this, then the velocity gained by this block will be higher than this. The velocity which is transferred to the other body on collision depends on the momentum which the body is carrying. The whole theory of that we're going to take up later. Okay, so that's why we define such a quantity, like we have kinetic energy, similarly we have a momentum. So on collision, momentum comes into picture. When we're going to study collision later, then we're going to deal with momentum in a greater detail. But for now, momentum is mass into velocity, momentum is represented by P, momentum is a vector quantity having direction same as that of velocity is good enough for us to get started with Newton's second law of motion. Okay, just one more thing. This is called as linear momentum because this velocity is linear velocity. When the particle is moving round and round in a circle, it is said to have an angular velocity, and then something called angular momentum comes into picture. But the study that we are doing till now is that body is supposedly moving in a straight line. That is a linear path. The velocity is linear, and this kind of momentum is linear momentum. That's it for now. Okay, so that will help us to get through the statement of Newton's second law of motion. I'm going to write the statement and then we're going to discuss it. Okay, so here it is. The rate of change of linear momentum of a body is directly proportional to the external force. Momentum is mass into velocity. This is momentum. Rate of change of momentum. Rate of change with respect to what? We have studied in calculus dy by dx is the rate of change of y with respect to x. Now here, with respect to what has not been specified, and in this kind of language, invariably it is always with respect to time. So rate of change of momentum would be dp by dt. Rate of change of momentum, that's how we write, that's what we learned in calculus. So rate of change of momentum of a body is directly proportional to the external force. So rate of change of momentum is directly proportional to the external force. That's what the first part is saying. External force applied on the body, and the change takes place always in the direction of the applied force. That means the momentum is changing in the direction of the force. They both are vector quantity. So whatever the direction is on the left hand side, same is the direction on the right hand side. So whatever the direction of force is, same is the direction of the change in momentum. And if we have to get rid of this proportionality and we have to turn that into equality, we have to bring a constant, k. So this is what is the mathematical form of Newton's second law. Rate of change of momentum of a body is directly proportional to the force, and the direction of the force is the same as that of the change of momentum. So this is how mathematically we can write Newton's second law. Okay, so this is the original equation of Newton's second law. Now let's look into it, what it is actually. Force vector is k into rate of change of momentum. Momentum we know is mass into velocity. We can replace p by m into v. So this gives us, now there's two term of differentiation, and this kind of differentiation we have learned in the calculus that we studied right in the beginning. Now if mass is constant, and that would be the case in most of the cases, mass remains constant during the motion, then this mass can be brought out from the differentiation. So mass can be brought out, and that is just dv by dt. And what is dv by dt? dv by dt is rate of change of velocity, and that is termed as acceleration. So force vector would come out as k into m into a vector. That means F is equal to k into m into a. And experimentally it has been seen that the value of k is 1. This constant that we thought would be a constant, that is indeed a constant, but that is of 1 unit. So k is equal to 1. Experimentally it has been seen. Experimentally you can verify if you apply certain amount of force on a body, and you can see what is the acceleration of that body. That both things can be measured easily, and the mass would be well known. So via experiment we can find the value of the constant, and that has been found as 1. So what we have at the end of it is F is equal to ma. This is the famous equation in physics. Force is equal to mass times acceleration. F is equal to ma. This is the simpler form of Newton's second law. It comes from here, but you have to always remember this, because there could be various variations of the Newton's second law depending upon whether the mass is changing or not, velocity is changing or not. But when the mass is constant, as we have done here, this is the simpler form of Newton's second law. F is equal to ma. And just to take a note, suppose mass would be changing. Suppose there's a truck, and the truck is carrying some water, it's a water tank, and there is some leakage. So as the truck moves on, the water keeps on spilling on the road. So in this case, the mass of the system is not constant, it is continuously decreasing. So in this case, if you have to apply Newton's second law, you cannot say that m is constant and bring it out of differentiation and come to F is equal to ma. F is equal to ma will not be valid. So whenever you will be using F is equal to ma, you have to know at the back of your mind that the mass of the system should remain constant, and initially whatever the cases will be dealing with, mass indeed will remain constant. But later on you will see another variation of Newton's second law in which mass would be changing. In that we cannot use it straight away F is equal to ma. And just to give you a little bit of insight here right now, what would be happening there would be this differentiation, both the terms are variable. So you have to use the product rule of differentiation. You have to differentiate is like this, keeping mass out of differentiation, you differentiate velocity. And then keeping velocity out of differentiation, you differentiate mass. That's what you do for differentiation. That's how you differentiate the product of two functions, when both the functions are dependent on the variable in terms of which you are differentiating. So mass is also changing with time, velocity is also changing with time, both are dependent on time. This is how the actual differentiation would be if the mass is changing. Okay, and there could be a third variation in which velocity is constant, velocity is not changing, only mass is changing. In that case, this term would be 0 if velocity is not changing. You will have v dm by dt. K is 1, so instead of m dv by dt, you will have v dm by dt. So these cases we are keeping on hold. So what we are going to start with right now is when mass is constant and we have a good looking formula, F is equal to ma. Okay.